Hello, everyone. Today I'll be presenting Chapter 7 of the book Fundamentals of Business Process Analysis, and the chapter is titled Quantitative Process Analysis. This chapter is about using data and mathematics to ensure, analyze, and improve business processes. In simpler terms, it helps organization answer questions like how long does our process take on average? Where are we losing time and money? And if we add one more staff or automate a process, what would happen? By the end of this presentation, I would have emphasized the main points and the main methods used for quantitative process analysis, from flow analysis to queuing analysis and simulation. So the chapter starts off by emphasizing the purpose and the importance of quantitative process analysis. In business process management, organizations always want to improve efficiency, cost, and consumer satisfaction. But in order to convince the decision makers or justify changes, they need to present measurable evidence and not just opinions. Quantitative analysis provides that evidence. It tells us how fast, how costly, how often, and how effective a process runs. It also allows for what if analysis, that is, testing how a process might behave under new conditions without having to change the real one yet. You think of it like running a stress test for your process before making expensive improvements. Chapter 7 is divided into three main parts, which is flow analysis, the queuing theory, and simulation. So flow analysis is a straightforward analytical method that uses averages, and queuing theory is a mathematical approach for systems with waiting lines, and simulation is a computer-based modeling approach for complex, realistic scenarios. Each method increases in complexity and accuracy, as I will be starting with flow analysis first. Flow analysis is the simplest form of the quantitative process analysis. It's based on breaking a process from individual tasks, assigning average times or cost to those tasks, and then combining them to find totals. The main goal is to calculate the cycle time, which is how long a process takes from start to finish, also the cost per case, and to identify critical paths or potential bottleneck. So the charter dives into how we can calculate cycle time. So for example, let's say a process has three tasks done in sequence. Task A takes 2 hours, and task B takes 3 hours, and task C takes an hour. The cycle time is just the sum of all three. And in this case, that's 6 hours in total. That's usually easy when tasks happen after one another in sequence. But in real life business processes, we often have decision points or parallel activities. And in that case is when the chapter goes in depth in decision points. So at a decision point, for example, a company which is responsible for either approving or rejecting a loan, the process itself can take different parts. So to calculate the average of the cycle time in such cases, we'd use probability weighted averages. So using the loan example, for instance, let's say 80% of the loan applications are approved in 10 hours and 20% are rejected in 5 hours. In that case, the cycle time is essentially 80% multiplied by 10 hours plus 20% times 5 hours, which gives us 9 hours. So weighted averages account for how frequently each branch is taken. The chapter also gets in depth with parallel paths, which happens when tasks happen in parallel. We don't add the times, we just take the maximum of the parallel branches because the process must wait until both branches finishes. So for example, if one branch takes 6 hours and the other takes 4 hours, then the total time is 6 hours, which is the longer of the two. And cycle time efficiency compares the value added time, that is the time that actually contributes to the product or service, and it compares it with the total time, which includes waiting, delays, and those. And the formula presented is efficiency is equals to value added time over total cycle time multiplied by 100%. So if a process has 3 hours of value added work, but it takes 12 hours overall, the efficiency is 25%, meaning 75% of the time is wasted on waiting or non-value activities. The CPM, which is the critical path method, identifies the longest path through which through a process, that is the one that determines the total duration. If any activity takes longer, the entire process slows down. So knowing and identifying a critical path helps us prioritize where to improve first. So Little's law is a simple but powerful relationship in process analysis, and it states that the average number of items in processes is equals to the arrival rate times the average cycle time. So let's say, for example, if 10 customers' orders arrive per hour and each takes 2 hours to complete, then on average, there are 20 hours being processed at any time. Little's law essentially helps estimate work in progress and identify overload situations. And lastly, the chapter goes explains about capacity and bottlenecks. And capacity refers to how much work a process or resource can handle per unit. And bottleneck is the task or resource with the lowest capacity. That is, it limits the overall performance of the process. So if one task can handle 5 cases per hour and another only two per hour, then the process can't go faster than two per hour. So fixing the bottleneck usually yields the biggest performance gain. The chapter also explains the limitations to flow analysis. While flow analysis is simple and intuitive, it has its limitations. It assumes all resources are always available, that is, no breaks and no downtime. It also ignores the waiting time caused by queues and delays, and it doesn't handle unpredictable workloads well. So while variability and waiting matters, we turn to queuing analysis. So the next section, queuing and analysis, helps us understand processes where cases wait in line for limited resources, like customers waiting for a customer service rep or a machine waiting for maintenance. Queuing analysis usually uses three key parameters, which are the arrival rate, how often new cases arrive, the service rate, which is how quickly resources can handle cases, and the number of servers, which are essentially resources available. The goal is to estimate the average waiting time, queue length, and the utilization. So the chapter gives us two queuing models, and the first is the MM1 model, which is a single server. The first M means arrivals and service times are random, and the second M means the service time follows an exponential distribution, and the one represents one server. And the second model is an MMC model, and in real business organizations, there are often multiple servers, like either like a team of customer service agents, and that's where this model is being emphasized on. The model is multi-parallel servers. The model is usually used to predict the average number of cases waiting, the probability that all servers are busy, and the average waiting time. This helps, managers and decision makers to decide how many staff members are needed in order to balance the speed and the costs. And in order to understand, the queuing analysis and its results, it's usually done through the utilization. So, for example, if the utilization is around 95%, that's being considered high, and it lets us know that the customers are waiting too long. And if the utilization is low, for like let's say 30%, it usually indicates that the staffs are underused. So the goal is to find like an optimal middle ground, which is often around 70 to 85%. Queuing analysis is used to help find that sweet spot. Also, the chapter also goes in depth by explaining the limitations of queuing theory. So queuing theory model often makes assumptions, for example, that arrivals are random and services have exponential distribution. Real life isn't always that neat. When processes are too complex or data doesn't fit standard distribution, then we use simulation. And simulation is the most powerful and realistic technique in quantitative process analysis. It uses computer models to mimic how a process behaves over time. By running thousands of simulated cases, we can measure the average and maximum cycle times, waiting times, resource utilization, and overall costs. A simulation typically includes a process model, which is usually in a BPN format, a business process notation. Also, an input data, which includes the arrival rate, resource pools, and probability, and the performance metric, like what we want to measure, either the cycle time or cost. And once the model is built, we can perform what if analysis. For example, what if we automate a step? What if we add an employee? The chapter breaks down the tools for simulation, including the BIMP, which is a web-based BPN simulator. It also makes mention of Extensim and Arena, which are more advanced commercial software, and CPN, which uses PetriNet for detailed modeling. These tools visualize process execution and generate charts and report automatically. Chapter 7 goes in depth in the best practices for simulations, and it involves running multiple iterations to account for randomness, also validating the model with experts to know the processes, and use real data whenever possible, either from system log or time studies. And finally, performing sensitivity analysis, which checks how small inputs affect the results. This ensures that the simulation is both correct and reliable. Although, as well, simulation also has its cautions and its limitation. They depend heavily on the accuracy of the input data and assumption. So if the inputs are wrong, then the result can be misleading, which is like a classic case of garbage in, garbage out. They can't perfectly model human behavior. So it doesn't account for fatigue, it doesn't account for multitasking and improvisation. So simulations are best used as decision support tools and not exact predictors. So here's just a quick recap of all the quantitative process analysis methods that were discussed in the chapter. And it started off with flow analysis, which uses averages and probability to estimate time and cost, and it's best for simple processes. And its limitations are resource limit and also ignores waiting and queuing. And the next method was queuing analysis, which uses math to model waiting lines and is best for processes with limited resources. And its limitation is that it needs statistical data. And lastly, as we recently mentioned, was simulation, which is a computer-based modeling for realistic what-if test, and is best for complex and dynamic systems. And its limitation is that it's data intensive and time consuming. So each method has its place from quick estimates to detailed forecasting. So, in conclusion, Chapter 7 teaches us that quantitative process analysis is essential for data-driven processes. It provides a structured way to measure performance, also tools to find bottlenecks, and the ability to test improvement before implementation. These techniques bridge the gap between intuition and evidence, which helps organizations to make smarter and confident decisions. Thank you.